What if the most dangerous object in our sky isn't an asteroid, isn't a comet, but the moon itself? Not crashing, not exploding, just drifting. A shift so small you'd never see it, a change measured in millimeters per second, but enough to rewrite Earth's tides, coastlines, and eclipses for centuries. We've tested planetary defense, we've smashed asteroids, we've talked about nukes, but none of that was built for something this massive. You clicked to find out if we could stop a moon impact. You're in the right place.
Here's the twist. The tools we've built for asteroids aren't designed for something 3,474 kilometers wide. If the moon's path shifted even a little, could anything we have actually matter? We'll break down why kinetic impactors like dart target small rocks, why a gravity tractor scales badly, and why just use nukes isn't a magic button. By the end, you'll understand the scale problem and how scientists actually keep watch on the Earth-Moon system. If a 1% change in the moon's velocity sounds tiny, why would it rewrite every tide, eclipse, and coastline on Earth? Start with the basics. The moon weighs in at about 7.35 times 10 to the 22 kilograms. Its diameter is roughly 3,474 kilometers. It loops around Earth at an average orbital speed near 1 kilometer per second, bound by Earth's gravity in a stable, elliptical path. That orbit is tight enough that small shifts in speed or distance change the balance of potential and kinetic energy. Push a little faster at the right point, and perigee rises. Slow it slightly, and perigee falls. That shift sets up everything else: tidal strength, eclipse timing, and even the long-term rhythm of how the orbit evolves. Now, compare that to a near-Earth asteroid like the one hit by DART. Those targets are tiny by planetary standards, often billions to trillions of times less massive than the moon. A small delta V, centimeters per second or less, can noticeably change an asteroid's path over months or years. With the moon, even a millimeter per second is enormous. Multiply that millimeter by a mass of 7.35 times 10 to the power of 22 kg, and you're talking about momentum that dwarfs anything we've ever put on a launch pad. Think about impulse. To change the moon's speed by 1 millimeter per second, you need to deliver around 7.35 times 10 to the power of 19 newton-seconds of momentum. If you tried to do it with rockets, you'd stack up a line of Falcon 9 class launches that runs into the billions, and that's being generous about how efficiently the momentum transfers. Convert it to energy, and a 1 millimeter per second kinetic change means about 3.7 times 10 to the power of 16 joules. For a rough scale, that's on the order of 1,000,000 times the energy released by a single Hiroshima yield device. But unlike a bomb, which releases energy in all directions, you'd need that energy aligned and efficiently coupled into forward motion, not heat, light, or vaporized dust. Let's ground it in orbital mechanics. The moon's orbital energy per kilogram is set by Earth's gravity, and its angular momentum keeps perigee from plunging too low. When you add a small delta V at apogee, you shave perigee down. That matters because tides scale with the inverse cube of distance. Shift perigee inward by even a fraction of a percent, and tidal forces rise sharply. Coastal high tides could run higher and linger longer. Estuaries might push storm surges farther inland on certain cycles, and tidal resonance in shallow bays could amplify the peaks. You wouldn't need a dramatic crash to stress ports, wetlands, and levees, just a subtle change in the beat. We already know the system evolves slowly. The moon drifts away by roughly 3.8 centimeters per year as Earth's rotation trades energy with the orbit through tides. That's a whisper of change spread over millions of years, and it shows how resilient the Earth-Moon setup is when left alone. But it also shows how small shifts accumulate. Nudge at the wrong time and direction, and the compounding effects show up not in days, but in decades and centuries. Long enough to matter for coastlines built to today's mean sea level and tidal ranges. Here's the catch. The tools we've built shine on small bodies. Kinetic impactors count on momentum plus ejecta to magnify the push, but that bonus doesn't scale to a lunar mass. Gravity tractors rely on a spacecraft's tug, which becomes meaningless against 10 to the power of 22 kilograms. Even the nuclear option runs into poor coupling in vacuum. You make a mess at the surface without moving the hull. The takeaway is blunt. A tiny tweak for the moon is beyond our current propulsion, fuel, and launch capacity by margins that aren't close. So if push it fails, what about cleverness? Tractors, swarms, or the nuclear card? What if we turned every kinetic impactor we've ever launched into a swarm? The math still doesn't budge the moon. Here's why. Kinetic impactors work on asteroids because momentum transfer adds up when the target is small. You hit a modest rock, you kick off debris, and you get a bonus push from the ejecta. Gravity tractors work by parking a spacecraft nearby and letting mutual gravity tug the object over long periods. Nuclear options use a standoff burst to heat and blow off surface material, creating thrust from ablation. On asteroid scales, each method gives you a measurable nudge with a lead time of years. The same playbook looks neat on slides, but it runs into hard limits when the target weighs 10 to the power of 22 kilograms. The scaling breaks fast. Momentum transfer that works for a 100-meter to kilometer-class asteroid vanishes when the target is 10 to the power of 19 to 10 to the power of 22 times more massive. A gravity tractor's force drops with the square of distance, while the tractor's mass stays tiny. So the tug becomes almost meaningless unless you wait longer than any mission can sustain. Nuclear energy in vacuum doesn't couple well. Most of it races away as radiation or heats a skin-deep layer, not the whole body. You can spend huge energy and still fail to change the moon's velocity by even a few micrometers per second. Take the gravity tractor. Around the moon, it's like a spacecraft tugging a freight train with dental floss. A mini-ton craft hovering a few kilometers above the surface might produce a force comparable to the weight of a sheet of paper on Earth. Keep it there, and the integrated impulse grows. But the clock you need is not mission length, it's geologic time. Station-keeping burns would eat propellant, solar storms would threaten hardware, and lunar mascons would make stable hovering tricky. Even with perfect control, you'd need time spans longer than recorded history for a tiny change, and that change still wouldn't register against natural tidal evolution. Kinetic impactors run into the same wall. DART's result highlighted the momentum enhancement, known as the beta factor, where ejecta gives extra push. That works because the asteroid's escape velocity is low and debris can fly away, carrying momentum. The moon's escape speed of about 2.38 kilometers per second is not high by planetary standards, but the scale of mass you'd need to eject to matter is absurd. You could carve fresh craters, throw plumes into space, and still fail to accumulate a useful fraction of the impulse needed for a millimeter per second change. A global campaign of impacts becomes surface landscaping, not orbital control. Now the nuclear standoff. Detonating near the surface creates X-rays, neutrons, and a flash that ablates the top layer. That produces thrust, but most of the energy doesn't translate into momentum. You'd scar the regolith, loft dust that settles back, and leave glassy patches, while the orbit barely twitches. Studies that examine nuclear deflection for asteroids assume targets many orders smaller than the moon and rely on coupling coefficients that already limit effectiveness. Scale those numbers to lunar mass, and you fall short by factors so large they stop being helpful metaphors. Could an external hammer do better? A captured large impactor or dwarf planet sounds like leverage, but you trade one risk for another. You'd need to place it on a precise intercept, control fragmentation, and manage fallout from debris. Every step adds new failure modes that threaten Earth. The safer option still fails to move the moon in a controlled way, and the dangerous option increases the chance of collateral catastrophe. Conventional planetary defense shines on small to mid-size objects. At lunar scale, the same methods turn into theater, with lots of activity and almost no orbital effect. So if we can't shove the moon, how do we know it won't drift toward us anyway? The real defense isn't force, it's measurement. The Earth-Moon system holds steady, and we verify that with laser ranging down to millimeters. Arrays left on the surface bounce back photons that clock distance changes with clocks and clean geometry. That data feeds models that catch subtle drifts long before they matter. So support the programs that track what we can actually deflect. asteroid surveys, follow-up telescopes, and compute time that turns dots into trajectories. That's where a nudge counts. And if you want the practical side of Delta V done right, next episode shows how tiny speed changes steer city killers away, using tools we already have.
Thanks for watching. If you enjoyed this journey through the cosmos, hit like, subscribe, and tap the bell. And when you're ready for your next space mystery, click the video right here.